introduction. In this project, this title is very long. I feel like I'm trying to bore you right from the start. In this project, we are trying to improve geological mapping by addressing surface infrastructure artifacts in remote sensing imagery. I will explain to you the problem and the project's objective more clearly in the coming slides. We started this project last December with this fantastic team that we have in D2T3. We have Jack Mon, senior data scientist, and Tom Carmichael, our chief data scientist. So the problem that we were trying to address is that in remote sensing is susceptible to artifacts such as dams and drills and roads. Here I have one example where we have I show how the presence of Beverly uranium mine and Heathgate Beverly camp influence the remote sensing data that we acquire at northern Flinders Ranges in South Australia. So such artifacts cause machine learning models to give us abnormal predictions. We have to remove these artifacts before we apply our machine learning models on them. So removing or masking is a solution, but an ideal solution would be to remove these artifacts and then replace them with realistic data. And that's the objective that we have in this project. This we call inpainting, and is what we are trying to do here for our surface artifacts in remote sensing imagery. Then inpainting is very commonly used in computer vision for reconstructing missing regions or undesirable parts of an image. In public, it's called remove people from your photo, and it's very popular among solitude enthusiasts and photobombed victims. Yeah, so there are challenges about using inpainting for remote sensing imagery. Once I go through remote sensing, you get an idea why it's challenging to apply inpainting to address surface artifacts. Remote sensing, basically, in remote sensing, physical characteristics of the land are monitored and measured by measuring the reflected and emitted radiation from the land, from a distance, usually by a satellite or an aircraft. So the Sentinel-2 data is the remote sensing data that we used in this project and is acquired by Sentinel-2 satellites. And Sentinel-2 satellites are equipped with an instrument we call multispectral imaging instrument, referred to as MSI. So in remote sensing, different materials have unique absorption and reflection characteristics that allow us to specify which material that radiation is originating from. So we can clearly say what minerals are or materials the radiation is coming from, and then this information can be used to map surface geology and identify compositional changes. So in the Sentinel-2 data, we basically 13 bands are acquired from visible range to near infrared to shortwave infrared ranges. So it's like 13 different bands. Excluding band 10, which usually is not as frequently as the other bands for land surface analysis, we get an imagery with 12 spectral bands. And then each band has a very different spatial resolution. Some have 10-meter resolution, some have 20-meter resolution. So what we did was that we upsampled all of them to a 10-meter spatial resolution. Here you see that we get an imagery with 12 spectral bands. And the area that we have used in this study is the North Flinders Ranges in South Australia. Mainly, specifically the Beverly uranium mine in the Basin Dam, which hosts several uranium roll-front deposits. Mainly because of its variational composition, such as calcareous roads and operating plants and mud pits. So for visualization, this is the Sentinel-2 spectral band, spectral imagery in that area. For visualization, we have made this RGB composite image, which basically uses band 2, 4, 8A, 11, and 12. So the red channel basically represents the hydroxyl index and is calculated as the ratio of band 11 to band 12. The green channel represents the iron oxide index and is calculated as the ratio of band 11 to band 2. And then the blue channel represents the vegetation index and is calculated as the ratio of band 11 to band B8 multiplied by the ratio of band 4 to band B8A. So this is just for visualization. The modeling is actually done on the 12-band imagery. So keep that in mind. So what we did was we tried to identify and mask all the regions with surface artifacts like roads, mines, dams in that areas, and this image shows all the roads and surface artifacts in that area. So keep that in mind because we'll get back to that. And so now I'll explain the inpainting model that I used. So diffusion models are a class of generative AI models that are capable of generating very high quality images. Text-to-image generation and inpainting are two typical applications of diffusion models. The diffusion model that we used in this project is called latent diffusion model, and the architecture is shown here. You see that there is a UNet inside its architecture. So UNet is basically receives an image and outputs an image. The architecture is very similar to autoencoder, except that there are connections in between the different layers. Right, so it's a very popular model in computer vision and has shown to be very useful for different projects. So ignore this part because this part is used for applications like text-to-image generation and not inpainting. Training this model is done in two phases. In the first phase, the UNet is trained to receive an image with a mask inside it, with a missing region inside it, and then it outputs an image with the reconstructed, with that mask region reconstructed in it. So that's the training of the phase one. In the training, UNet learns to reconstruct that masked region. In the second phase, the UNet is fine-tuned to using a diffusion-based denoising operation. So that basically makes the UNet more powerful. So we used this latent diffusion model, but like I said, there were some challenges. So the challenges that we faced was that, firstly, this latent diffusion model is designed for RGB images, but our images are of 12 spectral bands. And then secondly, the typical input to a latent diffusion model is an image of size 512 by 512 pixels, but our imagery is substantially larger. It's about 6,500 by 7,500 pixels. So to address these challenges, what we did was that we re-implemented multiple parts of the LTM. to accommodate images with arbitrary number of bands. And then we initiated this new LDM model with the weights from a pre-trained LDM model. Then we cropped small tiles from our imagery. So we didn't pass the whole image through the model. It wasn't possible. We cropped small tiles from the imagery from the areas that didn't have any surface artifacts, and then fine-tuned this LDM model. For training, like I said, there were two phases. The masking style that we used for phase one, which is training the unit, is, and then fine-tuning the unit are shown here. So this way we trained the model using our 12-band imagery, and then we used it for inpainting tiles that actually had surface artifacts. So here we have three tiles with surface artifacts. The mask that annotates the surface artifacts are shown here. Then what we do is we convert these masks into box masks because as per the training protocol of the LDM. Then we use these box masks to mask the tile, and then we pass these tiles to the LDM. Then LDM will inpaint the black region, the masked region. We replace that part with the output of the LDM, and then we make sure that the replacement follows a smooth transition from the original imagery to the inpainted region, guided by the original mask. So it's make sure this smooth transition from here to here. So here we show the final inpainted tiles for these original tiles that we have here. So we use this technique. So basically we first cropped 52 overlapping tiles from the regions that we specified to have surface artifacts. And then each tile is of size 2K by 2K, 2 kilometers by 2 kilometers. Then we passed all these tiles through the inpainting, and then we merged the inpainted tiles using feathering. So feathering ensures that there is a smooth transition from one tile to the adjacent tiles. So using feathering, we merge all the inpainted tiles, and then we integrate that merged inpainted tile with the non-corrupted regions around the corrupted region that we inpainted here. So here is that North Flinders Range, maybe a zoomed-in version of the Northern Flinders Range with surface artifacts, the original imagery. And then here is the masked region, the artifacts that were specified and masked. And then here we have the inpainted imagery after conducting inpainting. So there's definitely room for improvement. There are three things that we have been thinking about, three options. One is that to use during the training phase, use masks that are similar to what we see in our actual data set instead of using box masks. That will improve models' focus on the regions that are corrupted. But of course that would increase the training time for the model. Then another one would be to use a better tile merger algorithm, because sometimes occasionally we see like here we see some edge effects. So a better tile merging algorithm would be of course beneficial. And finally, to train an autoencoder with attention modules, we thought would be helpful to maintain better continuity in the texture. So we have noticed that in certain times there is some occasional discontinuity in the inpainted regions. So I have provided one example for you here to get an idea what happens. So here is one region with no surface artifacts. And what we did was that we made a fake road. We masked that fake road there, and then we did inpainting. And then now we can compare the inpainted region and with the original data. So what we see here is that here there should be more continuous like feature, or even here. So for these parts, we are thinking that an attention A unit with attention modules could perform better in those cases to have better continuity in the data. But of course, that means that we have to train the model from scratch, and that would take substantially much longer time than the 16 GPU days that we spent fine-tuning this model, the LDM model. But also keep in mind that the LDM model originally, the original architecture, has attention modules in its unit architecture, but the authors, the best model, pre-trained models that the authors provide doesn't have any attention modules. So there might be a good reason behind why they don't use attention modules in the architecture. So yeah, that's about it. I hope you find this helpful. Please let me know if you have suggestions, because we have just started this project and we are hoping that we can use it in our day-to-day projects. And yeah, if you have any questions, please let me know.
Thanks a lot.
Yes. I was wondering, is there an optimal amount of overlap for the feathering of your patches to get an optimal smooth transition? Is it like half?
No, yeah, that's a very good question. It's not half. I didn't really. So the overlap, the tiles that I selected were done just manually and just to make sure that I cover the surface artifacts. So sometimes the overlap is larger, sometimes the overlap is not that large.
Okay.
Yeah, but it's a good experiment to do and make sure. Yeah.
I was also wondering if you were to train it from scratch, how long would that take? You said 16 days on GPU time days using the pre-train. How much would it take for?
Yeah, I tried training the model from scratch for 3 days. While it was training, I checked like how the outputs look. It was no way close to merging. So I was like, maybe I should go with fine-tuning. So I think it would easily, of course it depends what GPU and hardware you're using, but I could guess that it could take like a month to train that.
Thank you very much for this interesting topic. Well, if I consider like instead of land to the bathymetric data set, we always encounter such type of problem. For example, multi-beam data with the single root data, we also see this type of anomalies with the artifact. But the thing is that would it be possible, like, to see any type of uncertainty how precise you are, like, to remove the artifacts in terms of scale?
Scale. Yeah, that's a very good question. So the way the idea behind why we chose a 2 kilometer by 2 kilometer tile was that we have enough texture in the tile. So I think it's always about like when deciding about the tile size. Is that your question?
No, I mean when you apply this model, you get some kind of uncertainty or the precision level. I meant that if it is possible to apply some to get or to generate some type of accuracy of the model.
Oh yeah. So this is very good point. In case I was just talking to you about it, like in terms of like if there is a structure that you can segment, and then you can compare the segmentations of the inpainted and the original data. I mean, just like the experiment that I had here. Like you consider a region that is perfect, it doesn't have any artifacts, you run your model on it, and then you compare these two, the outputs with the original data. You can do segmentations and compare segmentations to each other. That would give you a quantitative metric to compare them. But in terms of qualitative, I think you guys have a better idea. I basically generally visually look at it and see if it actually makes sense. One other thing is that I have worked on bathymetry. I have done inpainting on bathymetry before, and So there are like sometimes the artifact is so small that you don't really need an inpainting model to inpaint that region. There are methods in Python like called infill that just do a smoothing. It's basically averaging the surroundings and comes up with a filling for that surface artifact in that region. So you don't even need a model to use for those cases. But if the artifact is so huge that you cannot just focus and rely on the surroundings, then yes, in that case you can use inpainting models.
Okay. Sorry, I think we need to cut short in the interest of time. Thanks a lot.
Thank you so much.